Let us look at one more example under image restoration. Okay, so our main topic is still image restoration, okay, which, as I said, is an inverse problem. And we will look at what is called image super resolution. Okay, earlier what we saw was a deblurring problem, which was again ill-posed. Okay, and as you could see, right, a blurring problem was so very straightforward, right? Even if you had to do a space variant blur, you could do it so very easily, right, in the, early part of the course. But then deblurring, as you saw later, was an inverse problem, and then which was far more involved, right? And there were so many conditions that had to kind of go through in order to be able to get a clean deblurred image. Similarly, super resolution is again another sort of an inverse problem that comes under the umbrella of restoration. Okay, and super resolution refers to actually increasing the spatial resolution of an image. What this means is you would like to increase the spatial resolution of an image. Now, I mentioned spatial because there is also something called temporal super resolution, and we are not interested in that. Increasing the spatial resolution. So this deals with the task of improving the spatial resolution of an image. Okay, there is another task, what is called temporal super resolution, which means that if you've got like 30 frames per second video, can you increase it to 60 frames per second? Right, that's like a temporal factor of 2, right? You would like to increase it by a temporal factor of 2. Here, we are not interested in that problem. That is a different problem. We are interested in spatial resolution. As I said, right, under this is a restoration umbrella, you can have so many problems, right from deraining, dehazing, high dynamic range imaging, deblurring, super resolution, denoising, so many of them. Okay, the idea is to just look at a couple of problems. Deblurring we've already seen. I thought I'll also give you a window into the image super resolution problem, and then once you understand, right, so two such problems, then you would know as to what it entails to solve any of these problems. Okay, restoration. Now, increasing the spatial resolution. So what it actually means is that, let us say I have a lousy camera. Assume that I have a cheap camera, right? I don't want to pay much. I just take a cell phone, and then, it's a kind of a low resolution camera, low resolution image. And I would like to, bring it up to a higher resolution. So let's say it is M cross M, then maybe I want it to be 4M cross 4M. Okay, which means I want to go up by a factor of 4. Okay, you're going up by a factor of 4. Okay, something like that. And it could also be 2, it could be, 3, 8, whatever it is, right? So you want to go up by a certain factor. And how do you do that, right? Is what is this issue about, super resolution about? Okay, there isn't anything super about super resolution. What it involves is, right, just as there is let's say a high resolution image which you are not able to see. This goes through a degradation process, which is your camera. And the camera yields a G, which is actually a low resolution image. Now you want to put up, okay, so basically this is the degradation process, which we'll have to model, of course. Okay, like I said, the whole idea is to undo a degradation. So first of all, we should know what is the degradation process. Then you have to undo the degradation here through some kind of a restoration filter. Okay, degradation, and then in order to be able to get some F hat, which we think is approximately close to F, right? Where F is your input high resolution image. Now, this is unknown. Okay, we don't get to see this. So if you have a poor camera, you only get to see this LR image, which is of a much lower resolution. And you are saying that have some kind of a filter here, which will be a restoration filter. Okay, whatever it is, right? Some algorithm here which will take this LR image and then blow it up by a factor of whatever, 2 or 3 or whatever, in order to give you back a high resolution image. Now, by what factor can you go up and so on, right? It depends upon several things. We'll see each one of them one by one. Now, the need for spatial resolution is of course obvious, right? I mean, every one of us would like to, right? Even if you give me a high resolution image, you have a fantastic camera, I might want to ask, can I blow it up further by a factor of 2 or 4? Right? Simply because I simply like to see, even more fine details. Right, and this is something. Or you could have a very low resolution cheap camera, and you could ask, can I build a high resolution picture out of that, so that it matches the quality of my friend's camera, right? So he is paid more, I have paid less, right? I mean, I can't afford something very, very costly. I take a low resolution camera. Can I use some signal processing algorithms or image processing algorithms in order to be able to build a high resolution picture from this low resolution image. And the one that we are talking about, right, is, of course, we're talking about spatial resolution all through. Now, one of the need, right, arises because of cost, right? Cost is one thing, but then cost is not the only thing, okay? Why you would want to kind of do super resolution, because one thing is you want to buy a cheap camera and do super resolution. Other is noise, okay? Especially photon noise, okay? Because as we know, okay, even if let's say even if the manufacturing industry can really bring down the spatial resolution, right, of your sensor, let's say right here is where we are today, and suppose they say that we can manufacture something that can even be finer than that, and then later they say, oh, we can even go finer than that, okay? Now your manufacturing process may allow it, but somewhere, right, the photon noise will start to limit your ability to kind of go down. Not because you have a manufacturing problem, but then, right, because of the fundamental physics of the problem. As we know, right, each of these is like a bucket. Right? Each sensor is like a bucket which is trying to take in photons, and more the area of the bucket, then the more likely that we'll get enough number of photons. And if we try to reduce the sensor size too much, then what will happen is our ability to kind of capture enough number of photons in a given period of time, right? Because the exposure time has got to be small. We cannot make the exposure time arbitrarily large for reasons that we have already studied earlier. The illumination could change if you keep a long exposure time, or maybe there could be motion blur and so on. The scene could need not be static, and therefore, right, you can't expose for too long a time. And then if you have short exposure time, but then your sensor size is very small, then your photon noise rate is going to be very high, because the uncertainty in terms of the number of photons that you can collect is going to be higher, right? And therefore, right, noise could then put a fundamental limitation to what you can do. Now, this is how it all started, by the way, right? So the people that started super resolution started, right, with these things in mind. But now, right down the line, I'll tell you what is going on in super resolution as of today. Right? People are looking at far more difficult problems, especially right within the deep learning framework. But I think this introduction to super resolution that we are going to do, which is kind of simplistic, but then it will at least throw some light into what really awaits you, right, if you have to do a full-blown super resolution problem. And the other thing, right, that I've also wanted to say was, interestingly, right, one of the right, big guys in super resolution, initially, right, he was a person that actually said that why kind of one cannot do super resolution, and after a couple of years, he wrote a paper on how to do super resolution. And so such funny things in research do happen. Kind of, researchers can sometimes, right, guess things wrongly, and then they come back and then they sort of realize that, oh no, right, okay, that's not the case. Well, actually, I can do it. Okay, now. So the way to kind of think about, right, the super resolution problem is something like this. It assume that ideally, if you had a high resolution kind of a camera, right, that means, right, you're able to sample the scene very fine. Okay, so it means that, right, you're able to sample the scene in a very fine manner. Okay, so your spatial sampling, right, is very good. It's at a very high rate. That means your sensor size is really very, very small, and you're able to sample. Now, this ideal, right? Think of this as what you would get from a high resolution camera. Now, when you capture an image, the same scene, right? When you capture it with a low resolution camera, because of the fact that your sensor size is larger, right? In a low resolution camera, what really happens is 4 of these pixels, right? So these will map to 1 pixel here, right? That is what really happens. And then similarly, the next 4 would map to the next pixel. And then similarly, the next 4 will go to this, to the 3rd pixel. This will go here, and so on, right? So you have, suppose you are going down by a factor of 2. So suppose the spatial resolution between these two images differ by a factor of 2. That will mean that 4 pixels here get averaged to give you 1. Because, see, sensor after all is like an area, right? So if you have, let us say, if the individual intensities here, now what is the super resolution problem? If the individual intensities here were A, B, C, D, what you see here is simply A plus B plus C plus D by 4. Assuming that right, they're all being weighted equally. After all, the sensor area, we can assume that, right, it leads to an equal weighting of all the scene points, and therefore what you're seeing, right, is simply an average value. And you're saying, given this average value, give me A, B, C, D. So you can already see that it's a very, very ill-posed problem, right? So kind of this maps to something like, so if you want to write down a mathematical model for this, the simplest model that you can write is Y, okay, which will be your low resolution image. So LR means low resolution image, Okay, HR means high resolution image, or SR means high resolution image. Okay, now what we, or the super resolved image, SR means super resolved. And you can simply write this as D times X plus maybe, so right, if you have some noise and so on. But let's say if you have no noise, it's like D times S, X, where this D will be a downsampler come averager, right? So this has to be a downsampler plus averager. Okay, so what that really means is this matrix should have entries such that, right, it would average, okay, 4 of these values and then kind of map them to 1. So it's going to not only downsample, okay, right, which is the reason why between 1D and 2D, right, there is a difference. In 2D, it's a sensor area, it's a physical thing, it's a physical area, therefore it will average intensities. Okay, therefore when you talk about low resolution, we are also talking about a sensor size that's bigger, and therefore, right, there is an averaging effect. So that averaging effect needs to be captured by this D. Okay, so it's not only a downsampler, it's also an averager. Okay, it has to do both. And as you can clearly see, right, if you're going for something like, let's say a factor of 2, then maybe, right, if this guy is n squared by 1, and let's say, right, y will then be n squared by 4 cross 1, because it will have like n by 2 by n by 2. There will be the image size of y. If x is n by n, y will be n by 2 by n by 2. Therefore, if you stack it up as a vector, it becomes n square by 4. And therefore, right, D will then be n square by 4 by n square. Right? Okay, that will be the matrix that you will have. Now, in such a situation, right, one option, one of the simplest things that you can. So you can imagine that there can be many x's that can lead to the same LR. Right? So this is your LR. Okay, this is your original image, right? HR, which you would have liked to see. Now, as you can see, right, A, B, C, D, Y, I can even put B here, A here, D here, C here, and then I'll still see the same average. Therefore, you can see that there are multiple solutions, right, for this problem. There are multiple high resolution images that can map and give you the same LR. Okay, so in this case, clearly a solution exists. Okay, but then, right, okay, it need not be unique. Okay, it is not unique, in fact. And therefore, one of the things that you could do is what we did earlier, something like a min-norm solution. But then people have realized that min-norm, right, is not the one that really gives you what you would like to see. Okay, you need to do kind of more work. Okay. Now the kind of progress, right, that has happened is in terms of not just doing super resolution with one image, but then super resolution if you had multiple images. Now, that's why what we are going to talk about is what's called motion super resolution. Okay, what is called motion super resolution. Okay, there is also something called a single image super resolution and so on. Okay, and especially, okay, so for example, in such a case, min-norm solution could be 1, but that may not be so great. Okay, therefore, right, one can do some kind of an optimization with some L1 norm or the gradient of the image, and then have this cost just as we did for image deblurring and solve for the original image. Okay, right, that can give you something kind of better than what simply a min-norm solution can give. Or one could go in for something like a deep network, right, where you can train and then train for super resolving a single image. But what we are going to be focusing on is motion super resolution, because, right, given the background that you have, this is the one that you will understand the best. Okay, because this is really not a kind of deep learning course, and therefore, right, I don't want to bring in deep learning, okay, into this course. So motion super resolution. So what is the idea behind motion? Now clearly, right, if I take an image and if I try to interpolate it, if I take an LR, okay, now alright, right, let me first draw the HR image. Okay. I have the HR. Okay, now alright. Now let me just draw it like this. Okay, now let me first wipe this off. Okay, there is a reason. Okay, so let us say that I have a high resolution image. Okay, and corresponding to that, I have one low resolution picture. Okay, this is LR1. Okay, this is my original high resolution. Okay, this is what I would have liked to see. I don't see this. I see this. Now, if you would allow me to move my camera, right? Suppose I am able to move my camera. Suppose that's why it's called motion super resolution. So if I can take my camera and move around, the simplest thing, right, which you can do is do an in-plane translation, right? So if you were to do something like an in-plane, you could also rotate. You could also have an affine motion. You could have a homography, right? A complete 6D motion, whatever it is that you ideally can. I mean, theoretically you can have any of that. But just to understand the basics of super resolution, the best thing to do is to take the simplest of cases. Suppose you move, right, in whatever manner. Okay, move just fine amount. Move by a fine amount, right? You're not going to move a lot. You're going to move by a fine amount. Then what might happen is, right, you might actually look at this part of the scene. And for this, right, again, okay, if you try to capture an image corresponding to this, you will have another image here, which will be LR2. And as you can see, the average that average of the pixels that is going to happen here in order to get you a pixel intensity here need not be the same as what might happen here. For example, right? For example, okay, with this guy, okay, this might give you some average here, or average of some pixels, okay, in order to give you the first pixel here, right? And therefore, if you can capture multiple such observations, then you take one more, perhaps, right? You went there, okay, and then okay, you took one more high resolution picture, one more image, corresponding to which you will have one more LR3. Okay, all that you capture are LR1, LR2, LR3, because you don't see any of these high resolution pictures. Just moving the camera, right? So you're kind of sensing different averages of the scene. You're sensing all of them at a kind of a low resolution because you don't have a high resolution camera. But the idea is that with one image, low resolution picture, you can only sample the scene at certain points. But now that you are moving, right, the hope is that you are sampling, right, multiple points, right? You're sampling the in-between points that you would ideally like to sample. And so the idea is that if you can move like this, right, now can you kind of aggregate all this information through your LR images in order to be able to, you see, build up a high resolution picture. Because the idea is that under what conditions can you kind of say do it, right? Now clearly there is one condition. Okay, it doesn't always mean that super resolution is possible. For example, one condition under which super resolution is not possible despite camera motion can be explained like this. Suppose you are translating. Okay, let me say that, right, your original picture was here, and let's say this is your high resolution grid, and you captured an image, and you know that, right, and you know that these 4 pixels map to one, then these 4 map to the next, and so on. Now corresponding to this, let's say that you have an LR1. Now, if your motion in the high resolution grid is such that your next image, unfortunately, right, for whatever crazy reason, right, it gets formed here, let us say, okay, if it gets formed here, okay, now if the next image, okay, if you capture here, then what it will mean is, okay, you will be capturing this average, but this average is already captured by LR1 because, that is how LR1 was getting formed, and therefore, right, and this was already there in LR1, this is already there in this is not there. Okay, now this is already there, okay, and then whatever subsequently is going to come is already been captured by LR1. Therefore, your LR2 may carry nothing new. The idea is that you should sample some in-between points, right, and not the same set of right, grid pixels, right, or grid points that the first, let's say first sort of camera pose gave you. So as the camera pose changes, the idea is that you're capturing different averages and therefore aggregate all this information in order to be able to come up with a high resolution picture. Okay, that is the idea behind doing super resolution. So the way to kind of express this is to actually write it down as an expression where you have yi, which is the ith observation, to be equal to d. Now wi, right? I'm going to introduce a matrix wi. Okay, let's know, right? We should understand that all of these are vectors plus some, let's say, noise ni. Now for the time being, let's just throw the noise out. Let's assume that you have an ideal model. Okay, because once you bring in non-idealities, then again, right, things will change. But for the moment, right, let's just assume that, right, everything is nice. Okay. Now what is the role of so right, this we know already, right? This is a downsampler and averager. Okay, this is the warping matrix. Okay, this is the warping matrix. Now what this means is that, right? So what this means is here, right, when you took an image here, okay, corresponding to that you had LR1. Now so when you say that you're going to superresolve X, right? This is what you're going to get X, which is a superresolved version of Y1, in fact, because Y2 is coming from something else, right? Which is not the original X, right? So the idea is as follows, right? So what this warping will do is, right, it will tell you. So what you're effectively asking is the following, right? If I give you multiple observations, let's say, right, for a factor of 2, I give you 4 observations. What you're asking is, get me that X such that when I don't move at all, that means when I take my first picture, Wi is identity, and I get Yi to be downsampled and averaged values of X. Then I move my camera, therefore there should be some warping that I should apply on X so that I come here to this green area and average the pixels there in order to get my Y2, let's say. And then similarly, right, I should apply some other matrix W, let's say 3 on this original grid, because I may have gone somewhere else. After that, I could have gone somewhere here, let's say, and for which, right, I may have an LR3 and so on, right? So you need to, so each case you will have a certain warping matrix which is acting on the high resolution image, right? X. So this is acting on the high resolution grid. And after you have that, then you can downsample average in order to show the observation, in order to see the observation. So what you're effectively asking is, give me that 1x, okay? We are not asking for each of those warped versions. We are just asking for that 1x corresponding to LR1, that x, which is a high resolution version of LR1, which when warped will give me, which with no warp and downsampled and average will give me Y1, which when warped and downsampled and average will give me Y2, warped and downsampled and average will give me Y3, and so on. Okay, that is what is the optimization problem, right, which you're trying to solve. Okay, and on top of that, you can of course add other constraints on X and so on, which is your high resolution picture. Okay, now in the sense that in a regularization framework, the observation term that you will have is norm of yi minus, let's say, right, dwix norm square, right? In a sense, that is what you look at. Now we will kind of look at a very simple situation, right? We don't want to solve the superresolution problem in its sort of generality, okay, in this course, but I just wanted to show you a very simple situation. Instead of 2D, right, look at the 1D equivalent of this example of the superresolution problem. What will be the 1D equivalent? Okay, think that I have a sequence xn, right, which is a high resolution sequence, 0, 1, 2, whatever, right? Now what I have is basically a low resolution observation corresponding to this sequence x. Okay, this is your xn versus n. Okay, now let's say whatever it is of some length, n minus some length n, capital N. Now my first observation y1 of n, right, is coming as average of these two, average of these two, average of these two values, and average, and then right, go on, and finally average of those two values. Then my y2 of n, right, is like because of motion, right, I could have moved somewhere here. Okay, in the sense that I could be, okay, now wait a minute, right? So the idea is that I could be here, okay, and then right here I could be, and then here, and then I could be here. So I moved by a global motion, right, which is simply a constant, right? So I moved by some constant amount. Let us say, right, this is delta x or something. So if that is my high resolution motion, just as we said for images, right, you could have a 2D translation. Imagine that this is just delta x, right, in the time domain. Then what you are effectively saying is that y2 of n will then be the average of these two, average of these two, average of these two, and so on. And that gives you y2. Similarly, you can get y3 of n and the y4 of n, and so on, right? Now, right, you can get all of them, okay, in the same manner. y2 of n. Then let me put this as y3 of n. So you have like y3 of n, y4 of n, and so on. Okay. Now the idea is that, right, given these observations, what we would like to do is, we would like to kind of, get our x out. X is your high resolution sequence. Okay. So we are kind of looking at the 1D case. Okay, and right, and we would like to get our xn back. Now, before we can do that, right, so we need to understand as to how this model is going to look like. And now look at your w. Okay, now let's say w1 is simply identity, because right there you haven't moved at all, and it's simply an average of the original x values. What about, let's say, now right w2? Okay, w2 will have, let us say, if it is delta x2 is the motion. Okay, if delta x2 is the motion, then right, this is going to have minus 1 minus wx2, because now, right, because we are saying that we would like to arrive at these values by doing a linear interpolation, right? If it is 2D, then you would do a bilinear interpolation, but then in this case, right, it is going to be a linear interpolation. 1 minus delta x2, then right, 0, 0, 0, 0, then you'll have 0, 1 minus delta x2, right, 0, 0, 0, and then all the way up to 0, 0, 0, all the way up to 1 minus delta x2. Okay, this will be the form of w2. Similarly, w3, right, will have 1 minus delta x3. Okay, so in general, right, if you have any delta xi, so you'll have delta x3, 0, 0, 0, then 0, 1 minus delta x3, and so on. Okay, delta x3 and so on, right? So we know how to do this linear interpolation, right? What about your D itself? Now D is this special matrix, which is a downsampler and averager. Therefore, for the 1D case, it will be 1, 1, 0, 0, all the way up to 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, all the way up to 1, 1, right? At the final values. So when you look at y is equal to d, or yi is equal to d wi x, right? This is what you mean. So you're going to warp x by the warping matrix. Okay, so which means that you can get these in between values, and those will have to be averaged and downsampled, which is what this will do. See, for example, right? So when this acts on on an X, right? After, of course, in the warped X, then what it is going to do is it is going to average the first two values. Okay, in order to give you the first entry, then it is going to average the next two values, right? 1, 1, in order to give you the second entry, then the third entry, and then the final two entries, right? So that is how it is going to take care of downsampling as well as averaging. Okay, that's why we call this downsampler cum averager kind of matrix. And now, what the super resolution, right, entails is something like this. So let's say I have y1, I've captured one low resolution observation, that is simply, okay, dx. Okay, and now y2 is dw2x, because y2 will come from a warped version of x. Then you got y3 is equal to dw3x, and then we got y4, which is equal to dw4x. Okay, therefore, right, I mean, if you think about it, if x is, let's say, okay, so if you can write this up as y1, y2, y3, y4, you just stack up all the LR observations. Okay, so if you're going up by a factor of 2, okay, then your dwn, okay, let's write this down as, let's write this down as dw1, dw2, dw3, dw4, okay. Now each of these dwi's, right, I mean, as you can see, is of a size. So if this is, let's say, if you're down by a factor of 2, then your yi has a size which is n by 2 by n by 2, or n by 2 into n by 2, in fact, so which is like lexicographically ordered, so it will be n square by 4. Okay, x lexicographically ordered is n square by 1, and d is n square by 4 by n square. Okay, and therefore, right, clearly what this will mean is when you stack them up, this will become n square by n square, because you've got like 4 of them. Okay, n square by 4, n square by 4, n square by 4. So this becomes n square by n square. This again, because you have stacked up 4 observations, this together become n square by 1, and this is x, which is n square by 1. And now you can actually invert this matrix, provided, of course, you don't have kind of a pathological condition like the one that I mentioned, where LR1 and LR2 are exactly shifted versions of each other. Unless that happens, right, you will be able to invert this matrix. And suppose you call this as y is equal to dw into x, then you can compute x as inverse of dw, okay, this matrix inverse times y, right, and that will be x. So in a sense, right, the super resolution problem, we can define it in 3 words. It's like de-blurring, de-aliasing, and denoising. Now you'll wonder, why did I bring in de-blurring suddenly? Well, inherently, right, there is a blurring, okay, whenever you do super resolution, because you are downsampling. You are averaging, right? You are averaging 4 pixels. Any averaging is like blurring. Therefore, you are trying to de-blur. You are trying to de-alias, because you are trying to go from an aliased image to an unaliased image, right? Because your xn is unaliased in this case, the 1D sequence, whereas y1, y2 are all aliased, right? So de-aliasing and denoising, because of the fact that typically your model will be something like y is equal to dwx plus n, right? And therefore, you might also want to account for noise. So somebody asks you what is spatial super resolution in 3 words. It's simply de-blurring, de-aliasing, and denoising. Okay. Now, let me just give you a 1D example, okay, where let's say, right, which will kind of throw some more light on this, okay, in order to kind of look at how you can kind of perform this kind of a de-aliasing. Let me just take this example of mine. Okay. So now let's just look at this example. Suppose, let's say, right, in a simulation example, right, what you have, suppose you have in a simulation example, okay, suppose in a kind of simulation example, okay, we have let, okay, x of t is equal to sine 2 pi f naught t plus sine 2 pi f1 t, right? And the whole idea is, if we had samples of x of t, let's call this as xn, right? Then, okay, if I give you downsampled and average versions of xn, which will be y1, y2, and so on, okay, can you kind of reconstruct x from, say, y1, y2? If you just interpolate y1 and y2 to the size of x, the hope is that you will not be able to say retrieve your x back. The idea is, can you combine multiple low resolution observations like y1, y2, y3, y4, and so on in order to be able to reconstruct x?